Hello, my name is Rasmus Bøckman. I'm going to talk to you about how borehole thermal energy storage solutions can be a solution for small off-grid systems in the Arctic and polar regions. I've been living and working 9 years in Longyearbyen, both as a consultant and in Longyearbyen Lokalstyre. I've been working with infrastructure and mainly energy problems. Currently, I'm working in Multiconsult in Longyearbyen. So the agenda today is challenges of these off-grid systems, renewables and how to implement them, the importance of complementary storage systems, and I'm going to tell you a little bit about a response test, a thermal response test we did this spring. So most energy systems in the Arctic and polar regions are dependent on fossil fuels. Most of them are using diesel engines for electricity and diesel boilers for heat production. In Longyearbyen, we use a coal-fired plant that gets coal from a local coal mine number 7. Both of them are scheduled to be closed within 2 to 5 years. The delivering energy from diesel and coal has proven not to be very cheap the latest years. For communities that are based far away from other kind of infrastructure, the energy security is very important. If you have a period in the wintertime in Longyearbyen without electricity or heat production, within only hours you can have freezing conditions inside the houses. Of course, there are different qualities on the houses, but it only takes a couple of hours. And this high demand for heat is also something that is different from the mainland. When the coal mine and the coal power plant, which both are high consumers of electricity, when they are turned off, the balance between electricity and heat will be 75% heat demand and 25% demand for electricity as an average during the year. And in the winter time, when it's cold, the demand for heat will be even higher than that. So because of this, we've been looking into renewables as a new source of energy. They are cheap compared to diesel and coal. The main problems are that they are unstable. Of course, when there's no sun and no wind, they don't produce anything. And as you probably know, there's not much sun during the winter time. Our studies for wind has shown that there are most of the year we have stable, good wind conditions, but still we have, not every year, but now and then we have even longer periods without wind in the dark period of the year. And 4 to 5 weeks with clear black skies, minus 20 to 25 degrees Celsius is a challenge. You need to store mainly a lot of heat for those periods. So we've been looking into how we could use heat pumps to produce the heat more efficient. The problem there is that the seawater is so cold that you will have freezing on your collector, and then when you have enough frozen ice around your collector, it will float up and it can drift away. For ground-based heat pumps, you have the permafrost, which means you need to go very deep to be able to produce enough heat with a sufficient coefficient of performance. So because of this, we've been looking into more different kind of storage systems. And with today's technology, there's no batteries that can span those periods with a cost that is acceptable. Hydrogen is very is of course promising. There's no chemicals. You can produce both electricity and heat from them. You can use them for transportation and such. But the efficiency from electricity to electricity is very low. And you can also store heat in a big thermos, like a big steel tank that is insulated. You fill it with hot water when you have excess of hot water, and then you empty the hot water when you need extra heat. But this is only suited for day-to-day storage, maybe a couple of days, but not longer periods. Because of this, we've been looking into a borehole thermal energy storage system. So the main upside of these systems are the cost. They are way cheaper than any other way of storing energy. And when we've been looking into how we could incorporate this into the system, we've seen that they are sort of a facilitator, that such a storage system would be a facilitator to make other technologies more affordable and attractive. So when you dimension a wind energy system or a PV system to deliver a lot of the energy demand to your city, you would actually make them in a way so they overproduce for longer periods to be able to produce enough when there's not that much wind or that much sun. This overproduction you can then store into your BTS, your thermal system, geothermal storage system, to utilize when you need the heat. Which makes the economy of the windmills and the PVs much better. And of course, you wouldn't need to install that many windmills, which is an important issue in today's political climate around windmills. If you want to incorporate a hydrogen system to be able to produce electricity when there's no wind or solar system or wind or sun, or you want to produce hydrogen for the transportation sector, you can actually utilize the heat that comes as a byproduct from producing the hydrogen or from producing electricity from the hydrogen, because the energy loss that comes from producing from going from electricity via hydrogen to electricity, the energy loss from this process comes mainly as heat. And if you can take this heat, store it until you need it, and then utilize it, you increase the economy of the whole hydrogen system. Makes it much more affordable. Also for waste incineration, we have a difficulty finding incinerators that are small enough to fit our small community. You cannot run them on part load, because then they are not running clean enough. So you need to buy one that is too big and run it, and then you have overproduction for this period you run it, and then you cool it down again and let it stand and accumulate more waste. If you can collect this heat, store it until you need it, you increase the economy of this waste incinerator a lot. You can also incorporate solar heaters in your system. Solar heaters are like PVs, but they have a much greater efficiency. They produce heat instead of electricity, and they have a much higher efficiency, between 60 and 80%. You use this heat, store it until you need it, until the winter, and then you can use it. So because of this, we applied Svalbard Miljøvernfond for funding funding for a test run, a thermal response test in Longyearbyen. We got great assistance from Randi Ramstad and Henrik Holmberg in Asplan Viak, so doing some promoting of competitors here. We drilled down to 200 meters deep. We did this with a local rig. So this rig is normally used to bore holes for pile fundamentation of buildings in Longyearbyen. So we were very interested in knowing how easy it is to drill this deep with this kind of equipment. And it went really smooth, really easy, really fast. We didn't encounter any of the problems we anticipated. We found some methane though, which wasn't too good. Luckily it stopped blowing pretty fast, but that should be considered from if anyone wants to do other kind of tests of this kind. The groundwater came up to 41 meters deep, was very salt. 41 meters deep on this location is approximately sea level, which is interesting. And then we were wondering how the permafrost, so a frozen ground, would accept the heat when you try to heat it up. So we started doing this thermal response test. What you do is you put collectors in your hole and you start heating the fluid inside those collectors and actually start to heat up your hole. And you measure the temperature in the borehole and you measure the amount of energy that you put down into the hole. So, and the conclusions are that the ground is suited for a borehole thermal energy storage system. To build a system that is big enough to suit Longyearbyen, you will need approximately 50 gigawatt hours of energy capacity, and this would cost only 50 million Norwegian kroners, which of course is a lot of money, but it's still cheap compared to other storage technologies. What is open is if you should have a heat pump between the storage system and the district heating system, or you can use the money to build your district heating system to be able to handle lower temperatures than it does today. That is up to consideration, so should be investigated further. But I hope it was interesting for you to see our thoughts on how a BTS can provide many good solutions to Longyearbyen and other communities in the Arctic. And don't hesitate to give me any questions.